This video is about sound intensity and decibels. When we are talking about sound, we want to be able to get a measure of just how much of that sound is hitting you. We talk about volume, but it's nice to be able to quantify things a little bit on a scale that is a little bit more meaningful. We can turn anything up to 11, but that doesn't mean much. So intensity, if I have some kind of a sound source and it's going to put out sound waves, those sound waves are going to be distributed spherically. So if I am at some distance r, what I have is some speaker. Maybe I've got a speaker that is putting out let's go with 10 watts. That's a pretty good speaker. So I'm going to put out 10 watts of total power. Right? Watts are a unit of power. Those are joules per second. I'm going to put out a certain amount of power. I can say at a distance that power is distributed. I'm at some distance r from my sound source, and those waves, they don't care about direction at all, so they're going to go spherically outward. If I wanted to find how much of that wave is hitting this little window of this sphere, then I would want to look at an intensity. So I can say that my intensity is going to be a power divided by an area. I'm looking at a sphere, and the area of a sphere is 4 pi r squared, is the surface area of a sphere, which means the intensity at this radius is going to be 10 watts over 4 pi r squared. This will give me units for intensity of watts per square meter. That energy is somewhere. It has to go somewhere. It can't just disappear. A little bit before, that wave was smaller. It hadn't traveled as far, so we'll call that one little r. So this is intensity 1 is power 1 over area 1. Intensity 2 at this inner radius is going to be 10 watts over 4 pi little r squared. The intensities are different. If I stand closer to my speaker, it's going to sound louder because r is smaller. At the bottom, my fraction is smaller. The whole thing's bigger. But the power delivered by the speaker hasn't changed. So I can look at this equation and say power equals intensity 1 times 4 pi r1 squared. Over here I can say the power delivered by the speaker is intensity 2 times 4 pi r2 squared. And the power by that speaker has to be the same, which tells me I1 times 4 pi r1 squared is going to be equal to I2 times 4 pi r2 squared. I can cancel my 4 pi's, they really don't matter much, and I have this nice equation that relates my intensities. And it's an easy one to work with. So I have my intensity is power over area, and then I1 r1 squared equals I2 r2 squared. These intensities usually carry numbers that have a trailing term, like a times 10 to the negative fifth, things like that. So we want to be able to talk about sound level, which is a little bit different. Sound level takes the idea of intensity and fits it to a logarithmic scale. So what I'm doing now is saying I want a number, instead of having 4.3 times 10 to the negative fifth watts per square meter, is kind of cumbersome. Instead, I would like to change that intensity into some other value. The value that I'm going to work with is going to have units of decibels, lowercase d, uppercase b. And like I said, this is a logarithmic scale, so when you double your number of decibels, you are not doubling your sound. We need a reference point for this to work. So I'm going to write this intensity in watts per square meter, and I will write a decibel value next to it. I can start you off with an equation that looks like this. My decibels equals 10 times the logarithm of I over I naught, where I naught is 10 to the negative 12 watts per square meter. I can do that, but nobody really wants to mess around with logarithms, and definitely nobody wants to go backwards and solve this thing out. So we can do this a different way, and that'll be helpful. If we have an intensity of 10 to the negative 12th watts per square meter, we are assigning that a decibel value of 0. This is called the threshold of hearing. And for the most part, this is the quietest sound we're going to hear. It's not 0, but you have to have enough of a sound to be able to hear it. If I increase this by a factor of 10, so 10 to the minus 11th, then I'm going to increase this by 10 decibels. I have gone times 10 over on this side. I've gone plus 10 over on this side, which means if I go to 10 to the negative 10th, I'm going to add another 10. That's 20. So times 10 plus 10. I'm going to make a couple of jumps. What if I go 10 to the negative 7th? I have gone here times 1,000, which is times 10 to the 3rd. So over here, I'm going to add 30. 10 to the 3rd adds me 30. This is going to be 50 decibels. I can work backwards too. What if I have 10 to the negative 7th and I want to go 10 to the negative 8th? Well, now I am dividing by 10. So to get there, I'm going to subtract 10 and be back at 40 decibels. This doesn't get you all the decibel values, it just gets you kind of the whole numbers of 10. So I'm going to fill in a couple of those gaps. I do want to point one thing out. This is 10 to the negative 12th. What if I go 10 to the negative 13th? So I had this, I'm dividing by 10. My rule says here I must be subtracting 10, and that's exactly what happens. This is negative 10 decibels. The decibel scale can go negative. Now the in-betweens. Halfway between, let's say 40 and 50. If I want to go up by 5, so I want to go to 45 decibels, then what I'm doing here is multiplying by 10 to the 0.5, which is the square root of 10, which is about 3. So I will have a 3 times 10 to the negative 8th watts per square meter is going to give me about 45 decibels. It's not as exact as plugging into this equation, but the only times that you're going to come across this are going to be with multiple choice questions where the right answer is in front of you. It's good to be able to see a number and recognize where that falls. If I've got a number like 5 times 10 to the negative 9th, for example, this is watts per square meter, I would say I can find 10 to the negative 9th watts per square meter. I can find 10 to the negative 8th watts per square meter. And those aren't too bad to do. 10 to the negative 9th, I know my zero level is 10 to the negative 12th. I've gone up 3 jumps, which means this must be 30 decibels. I'm going up by another 10, so this must be 40 decibels. I am at 5 times 10 to the negative 9th, so if I have my in-between spot, and say 3 times 10 to the negative 9th watts per square meter is going to be 35 decibels. I'm at 5, so I must be somewhere between 35 and 40. And it may well be something like 37 decibels. It's not super precise in the sense of giving you decimal places or anything like that to figure that out, but it is giving you a range of answers that, if you are doing a multiple choice test, will get you close enough to be able to tell which is correct. One more piece to this. A common question that comes up with this is, I'm standing at this location 10 meters from a speaker and I hear a 70 decibel sound. What is my sound? How many decibels at 100 meters? I know the equation that I want to use is I1R1 squared equals I2R2 squared, but these are not I values, not I. This is something different. So what I would need to do would be to take that 70 decibels, convert it to watts per square meter. 70 decibels, 10 to the negative 12th watts per square meter is 0 decibels. I've gone up to 70 decibels. So this must be, I'm going up by 7, so this is going to be 10 to the negative 5th watts per square meter. That is my I value. So 10 to the negative 5th watts per square meter times 10 meters squared equals my new intensity times 100 meters squared. I find my new intensity, and then once I've got my new intensity, I'm going to have to convert that back to decibels to be able to solve this. I can't do this one directly. I have to take the roundabout way of getting there. But that's it. That's sound level and intensity and decibels in a way that is hopefully not any kind of scary.